Good morning! Hey guys, and welcome to another awesome lesson. We are talking today about how we are made up out of stardust and bonds and elements, so let's dive right in. I hope you like the video that I put into the section before this. I just think it's so amazing to think that stars are these forges that are out there, that are constantly just forging new elements out of the stuff of the universe and making it possible for life to exist among many other things. So we understand that every physical thing in the universe is made out of matter. And for our understanding, because we're not a physics class and don't need to know exactly what matter means, for our understanding, we're going to understand matter as being made up of tiny particles that contain different amounts of energy and behave differently based on the amount of energy that they have. So everything in the universe is made out of energy, and that shouldn't really surprise you because when we talk about biology up to this point, we've talked about how energy flows between organisms, and we've almost already talked about organisms as being sort of an energy currency. So there's energy flowing through everything, and everything has different levels of energy in different states. The basic unit of matter is the atom. So the atom is going to be basically our building blocks when we talk about these different units of energy. They are going to make up most of the big structures that we're going to be talking about. The atom consists of three different types of subatomic particles. These are the proton, which has a positive charge, the neutron, which has a negative, which has no charge. Whew, got to be careful there because neutron sounds like negative, but it really just means no charge, kind of like neutral, the word neutral, and electron, which has a negative charge. So if we look at the structure of the atom, we can see that the neutrons and the protons are forming together into the nucleus of the atom. They're tightly bound, and they are surrounded by these clouds or shells or orbits, however you want to refer to them. I'm going to be referring to them as shells because that's how we're going to be talking about them, of electrons that are going to be kind of orbiting around the nucleus. Okay, so we can notice that the positive charge is all kind of condensed here in the middle, and the negative charges are on the outside. Now, I do want to say that this is a model of an atom, and of course, when you do things in science, it's important to model stuff because we need to kind of get a concept of what's going on. But a model is not the most accurate view of these things, and I just want you to understand that even though we might picture an atom this way, this isn't necessarily what atoms really look like or exactly how they behave or are structured. This is just an easy way for our human brains to understand something that we are never going to be able to see with our human eyes because we have not evolved to be able to see subatomic structures. I guess you could say sadly, but honestly, if we saw the world in subatomic structures, it would probably be overwhelming and kind of terrifying, sort of like when Ant-Man goes into the quantum realm. So maybe it would be cool, but I also think it would be kind of scary as well. So the protons and nucleus again form the nucleus of the atom. This is different than the nucleus of a cell, but it is in the center, which is why we call it the nucleus. And surrounding the nucleus are these electrons. We've established that. Now, if there are more protons than electrons, the atom will be unstable and have an overall positive charge. If there are more electrons, then it will have an overall negative charge and will be unstable again. If it has an equal number of protons and electrons, then it is more stable and it has no charge. Okay, the neutrons again don't contribute to the charge of the atom, but they do contribute somewhat to its behavior, and we're going to talk about that in a little bit. Now, before we go on, it's important to understand that because protons are part of the nucleus, they are not going to be gained or lost easily. Okay, so protons are kind of the essential characteristics of the atom in the same way that your personality is relatively fixed. I don't know if you guys have a knowledge of this, or if you've studied this yet in psychology or anything else like that, or if any of your teachers have told you, but personalities of people are relatively fixed. This is something that's kind of fixed throughout your whole life. Your personality never really changes very much. However, your behavior in certain situations can change depending on the situation that you're in, but you have kind of a spectrum that you're going to stick to because of your personality, right? And so what I'm basically trying to say is that the protons are kind of like the personality. The number of protons don't really change in an atom, but the situation that the atom is in can dictate its behavior along kind of a certain spectrum. But that spectrum has a limit, and that limit is determined by the number of protons. So the protons kind of defines what kind of atom we're talking about. It's kind of the essential part. Okay, and we call this an element. An element is an atom with a particular number of protons, and it makes it behave a certain way and have certain properties that it just couldn't have if it had a different number of protons. So this is what we mean when we talk about elements. And examples of elements are hydrogen, nitrogen, oxygen, stuff like that. Now electrons, on the other hand, can be easily gained or lost or shared between atoms. Electrons often determine the stability of the atom and whether the atom will seek out other atoms to form bonds or remain isolated and content. Okay, so I want you to think about human relations, right? Okay, so in a human relationship or interaction, if I'm feeling stable, okay, and I feel mentally and physically stable, I feel supported and loved by those around me, I'm not going to really feel necessarily the need to reach out to others for comfort or to lean on other people, right? I might feel somewhat independent and good and strong and good to go, right? But if I am feeling down or sad or lost or confused or something like that, mentally and physically, then I'm going to start reaching out to other people for those relationships and those bonds. And that's kind of how atoms work as well. So if atoms have a good number of electrons that balances out their protons and they're feeling stable, they're not going to look for each other or form many bonds with each other. But if they don't, if they have not as many electrons as they need or as they need or too many, they're going to start looking for other atoms in order to form bonds. So this is what I mean when I say electrons often determine the stability of the atom and whether it will seek out bonds to be content. Now, if we look in a little more detail, we can see that the electrons form around the nucleus of the atom in what we call shells. And we can see that the shells are going to contain a certain number of electrons. Now, in biology, we're really only concerned with the first 3 shells of an atom. The inner shell can only contain 2 electrons. That will complete the inner shell of any atom that we look at. The second shell can contain a maximum of 8 electrons, and when it reaches 8 electrons, it's stable. And the third shell can contain a maximum of 8 or 18 electrons, depending on the examples we're looking at. And if it has either 8 or 18, depending on the example, it is stable. Any less or more than these numbers of atoms in these of electrons in these shells are going to make it unstable and want it to go looking for bonds. The outermost shell of any atom is called its valence shell, and this is actually the shell that's going to determine the behavior of the atom and its interaction with other atoms. So the valence shell is going to be this one right here for this atom, the outermost shell. And the valence shell here, we can see it has 18 electrons, so it needs 18 electrons in order to feel stable. If it has less than that, then the atom is going to go looking for bonds, and it's always going to form bonds with other atoms using its valence shell. The valence shell is, in other words, kind of like the hands and arms of the atom. It's going to be what they use to kind of reach out and hug another atom, right, if they need comfort or protection or stability. So the valence shell needs to be complete in order for the atom to be stable. If the valence shell is not complete, if it's missing 1 or more electrons, then the atom is unstable and will search for other atoms. So it's important to note before we go on that the outermost or valence shell is not always the third shell. Some people tend to think this when they see this example, but some atoms have fewer or more than 3 shells. To determine how many shells that they have, we have to look at the total number of electrons they have and how many shells that they have. So how do we figure this out? Well, we look at the periodic table of elements. In the periodic table of elements, for each element, it will tell us the atomic number, which is the number of protons, and also number of electrons, because it should equal the number of protons, the mass number, and the element symbol. So in order to tell whether or not the atom is going to be stable, we need to look at all this information. For example, if we look at carbon right here, we can see carbon has an atomic number of 6, which means it has 6 protons and 6 electrons. We can see its name. We can see it has an atomic mass of 12, which means that its combined protons and neutrons together equal 12, which means if it has 6 protons, it means it has 6 neutrons. We'll get to that in a little bit. And we can tell what the name is again. So using this information, we can calculate the number of protons, electrons, and neutrons. So I do this down here, right? So we can tell immediately as an atomic number of 6, so 6 protons, and that means it has 6 electrons as well. To find the number of neutrons, we need to take the mass number, which is around 12. I basically just rounded down to the nearest whole number. And I subtract away the number of protons right here, which is 6. So 12 minus 6 equals 6 neutrons, right? If you're confused about that, just make sure you look back at the mass number where I said it was the number of protons and neutrons combined. So to figure out the number of neutrons, all we have to do is subtract away the number of protons from the mass number, and we know how many neutrons there are. So now I need to figure out how many electron shells my carbon atom has. It has 6 electrons, so I know that 2 can fit in its inner shell, as we saw in this diagram up here above. Only 2 can fit in the inner shell. I need 8 for the next shell, and either 8 or 18 if it has a third shell at all. Let's check it out and see. So for my first shell, I can fit 2 in the shell, okay, so I have 4 electrons remaining. So if I take those 6 electrons I started with, and I put 2 in the first shell, in the inner shell, then I have 4 remaining to distribute. Now, 8 are supposed to be able to fit in the second shell, but I only have 4 left. So I can put those 4 into the second shell, but that means that my second valence shell, because it's in my outermost shell, it's my valence shell, is only half full. It needs 4 more valence electrons to complete the second shell. So, okay, there's 2 things I figured out here. One is that carbon only has 2 electron shells. How do I know that? Because I took the 6 electrons and I distributed them into the shells. Only 2 could fit in the inner shell to complete it, and I only had 4 out of 8 for the second shell. That means that the second shell is the outer one, and it's only half full. That means that carbon needs 4 more binds, or valence electrons, to complete its second shell, so that it can create up to 4 bonds with 4 other atoms in order to become stable and to complete that shell. So this is the reason why carbon is the backbone for almost all living things. When we look at most molecules that define living things, we can see that at their centers they have a carbon backbone or structure in the middle, and then all the other elements, the only ones you can see here are hydrogen, but there's also oxygen and all the others, are going to be supported by this central carbon structure. Carbon can make very strong bonds, especially with itself, and makes the perfect element to form long chains and backbones. So this is almost, carbons in this case are almost acting like little Tinker Toys, right? They're connecting together. I don't know if you play with Tinker Toys, or, you know, there's those magnetic ones and stuff, but basically it's like Legos. And you can imagine the carbons are these like little central Lego pieces, and off of those central Lego pieces you can build all sorts of stuff, depending on what shape of the backbone or foundation of carbon you've laid down. The little lines here just representing bonds between the carbons and these hydrogens and other carbons, and we'll talk a little bit about bonds here in a second. So, but anyway, the big point here is that carbon can make up to 4 bonds with 4 other elements, and especially strong bonds if it's carbon, and therefore makes the perfect backbone for most larger molecules. Okay, and this also leads to a lot of diversity. I mean, if you look at it, these are very different shapes of molecules, and there are many, many more that can be achieved using carbon. So basically it's like Legos, but with elements. Okay, so the 6 major elements necessary for life, including carbon, are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. I always remember it by remembering schnapps, which is the typical way that people remember it, C-H-N-O-P-S. You can remember it in any way that you would like to. If you can figure out a better arrangement of these letters in order to better remember it, please go ahead and let me know. I would love to know what you come up with. But these are the 6 major elements necessary for life. Carbon's going to be the backbone, and all these others are going to be built off of carbon. Now, let's talk about the bonds that are actually joining these elements together. There are 3 types of bonds that exist between atoms, and each is formed in a slightly different way. The first is covalent. These are the strongest bonds. Covalent bonds happen when 2 atoms with incomplete valence shells come together, and they share electrons in order to complete their shells. So we can see here that these 2 atoms are coming together, and we're just going to assume they have an inner shell of 2 electrons already filled, and we know that they need 8 to complete this outer shell. They have 1, 2, 3, 4, 5, 6, right? Or, and this, yeah, they need 8 to complete this, okay. So this guy right here naturally would have 7, and this guy right here would naturally have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, right? And they come together and they start sharing. Now, because they're both sharing their 7th electron, it actually stays in the same orbit and counts as the 8th electron in the shell. So if I counted them with this sharing going on, 1, 2, 3, 4, 5, 6, 7, 8, and if I counted this one, 1, 2, 3, 4, 5, 6, 7, 8. The point is that these electrons can be counted for both atoms now because they're sharing them. This is a very stable bond. You can think of this as being kind of like a relationship between 2 people who put an equal amount into the relationship. Both are fully committed and both are getting a lot out of it. This is a covalent bond. These bonds are going to be formed between atoms and are going to stay very strong for a long time. Ionic bonds are a second type, and these aren't quite as strong as covalent bonds, but they're stronger than others, other different types of bonds. An ionic bond happens when one atom goes ahead and donates or permanently gives one of its electrons to another atom, and then they start having an association because of a charge differential. And let me go ahead and show you how that means. So we go ahead and we start here with sodium and chloride. And if we look at sodium and chloride, we can see that in chloride's outermost shell, its valence shell, it has 1, 2, 3, 4, 5, 6, 7 valence electrons. It needs one more to complete the shell. In sodium has only one electron in its outermost shell, which means it would need 7 in order to complete it. Now they could do some sort of sharing thing, but instead of doing that, sodium says, well, that's ridiculous. I don't want to have to share so many electrons with chlorine, so here, you can just have it. And so sodium just gives this electron to chlorine. Now because of that, sodium gives away its electron. And I don't know, this diagram is actually incorrect now that I'm looking at it, because sodium stays positive. If you get rid of an electron, you're getting rid of a negative charge, so it stays positive. So ignore that. It stays positive. And then what happens to chlorine is it becomes negative because it's received an extra negative charge. Now because sodium is now positive and chlorine is now negative, the sodium is going to be attracted to chlorine, just like the positive and negative ends of a magnet are attracted to each other, right? So positive and negative attract, opposites attract, and therefore they kind of stay close to each other. But again, they're not sharing the electron. Chlorine took it, right? Chlorine has it now. It's just that they're sort of bonded by this gift. It's almost like, you know, you make a new friend, you give them a gift, and they're like, wow, this is a really nice gift, and then you guys start hanging out, right? It's not like you're sharing the gift, you gave the person the gift, right? But this has created a bond of friendship between you. So this is a fairly stable bond. It's not as stable as a covalent, but it's pretty stable. The last one is a hydrogen bond. The hydrogen bond is going to form when there are very slight charge differences within the same molecule. Okay, so for instance, when we look at, now up here we're only looking at atoms. So down here we're looking at molecules because we have hydrogens bonded to oxygen. These are two water molecules. You have one oxygen bound to two hydrogen. That's why we call it H2O. This is a molecule of water, and this is a molecule of water. And we can see that within this bond, oxygen is actually kind of hogging all of the negative charge, right? And so it's one molecule, but oxygen is more negative, and the hydrogen ends are more positive. And so what happens is that the two molecules start to become attracted to each other because of that negative and positive charge. Now, they're not sharing anything. They didn't give each other anything. They just happen to naturally have a positive and negative charge, and so they kind of stick together like magnets. This is the weakest version of the bonds that we're going to look at. Because they're not giving, they're not sharing. It's just that they happen to kind of be slightly attracted to each other, kind of like the opposites attract thing. You know, you might have some crush on somebody. It's not like really serious, but you have a crush on them, and maybe they're into different things, and they seem kind of wild and exciting to you, and so you're like, ooh, that's kind of neat. But you know, it never really forms into a very strong relationship. You just kind of maybe hang around each other every now and then, or something like that. That's a hydrogen bond. Okay, and I do want to stress this. We call molecules that have a positive and negative end polar molecules, right? And so that's going to become important later on. I don't know why I didn't bold it here, but they are called polar molecules. And so just kind of keep that in your mind. Hydrogen bonds are bonds that form between polar molecules, molecules with a positive and negative end. Now, when atoms bind together, they form molecules or compounds, as seen up here. These are actually really compounds. We call them molecules, really. You'll find that these terms become kind of interchangeable in everyday language, but officially, molecules are more than one atom of the same element bound together, like O2, which is what we typically breathe, right? Oxygen gas. And then compounds are going to be atoms of different elements bound together, like NaCl, which is sodium chloride, which makes table salt. Which is what the example we saw earlier with the ionic bond. So all living things are made up of a mixture of molecules and compounds, and just for the purposes of this class, for the rest of the class, we're basically going to use molecules to kind of cover everything. So yeah, okay, maybe some things are officially a compound, but we're typically going to refer to them as molecules. Now, the last thing we need to mention here is isotopes. An isotope is an atom of a certain element that has a different number of neutrons than the normal atom of that element. So if you look up here, carbon usually has a mass number of 12. Right? And 6 protons, 6 neutrons. Okay, but carbon-13 here has a mass number of 13, and we can see it has the same number of protons because that's what makes it carbon, but 7 neutrons. And carbon-14, again, has 6 protons, same number because that's what makes it carbon, but it has 8 neutrons. So what's this doing? So what? But neutrons don't contribute to the charge. How do they change the behavior of these elements? Well, even though neutrons don't contribute to charge, neutrons do contribute to the behavior because if the atom has too many neutrons, it's going to start giving off energy. Think of it this way. When you try to carry too many boxes all at once, or bags, like if you're going on vacation, you're like, I just want to shove everything in my car and just go, right? And so you try to carry out all the bags of the car in one trip, and you're dropping stuff left and right, and it's not going well. That's kind of what's happening here with these atoms. If they're carrying too many neutrons, they're going to start dropping particles. And when they start dropping particles, they're dropping energy, right? And so this leakage of energy is known as radiation. That's what radiation is, and it can be very dangerous, as we know from pretty much every movie. We see radiation come in, giant monsters, deformations, all this sort of stuff happens because of this leakage of energy and these isotopes of different elements. And this is how Dr. Simard in her tree research was able to track the carbon that was going through the plants, because she was able to use her Geiger counter, her radiation counter, in order to see where the carbon was going. It's also very useful for being able to date certain trees, and I don't mean dating them as in, hi tree, let's go out to dinner at TGIF, because it's gonna be lit. No, it's what it is when we say how old the tree is, right? And we can use carbon-13 in trees in order to date them up to around 50,000 years. After that, we have to use different elements because carbon-13 will degrade in that time and will no longer be useful for dating. So that is all I have for you guys. Wow, that was a lot. So we learned, okay, so let's do a quick recap, all right? All things are made out of matter. The basic unit of matter is the atom. The atom is made out of 3 subatomic particles, and the type of atom or element is determined by the number of protons. Its behavior is determined by the number of electrons. Atoms have various different numbers of electrons. This determines whether or not they will create bonds with one another. There are 3 kinds of bonds that occur between them: covalent, ionic, and hydrogen. And carbon is really good at making bonds with all sorts of other elements and really great at making backbones of more complex molecules and bonds. And finally, there are isotope versions of different elements that have different numbers of neutrons. Now, I know this was a lot to take in. Please feel free to watch this video over and over again if you don't find it too annoying or, terrible. And please feel free to email me with any questions that you might have. At this time, go ahead and begin the assignment. That is the Google Doc here below. And remember that it is going to be due by next Wednesday, October the 21st at midnight. Thank you guys so very much for your patience and listening to this video. I hope you guys have an excellent day, and I can't wait to see you guys next week. Take care.